Okay, so good. So let's come back to the class. Stop the other discussion that we were having, and let me also close the chat so that I don't see it. Okay, good. So okay, so this is lecture 3 on Laplace transforms, right? I think I started it on Thursday. We had a class yesterday, and today also Laplace transforms. Tomorrow, not tomorrow, Thursday also Laplace transforms. And let's see. Okay, so today I will also show a very simple IVP by solving using Laplace transforms, which I had hinted at yesterday. Okay, so let me start sharing the screen and let's start with the lecture. And as usual, one of you could confirm that you can see the slides.
Yes, sir.
Yes, sir.
All right. Okay. So see, the keyword is not changing. I have nothing new to say here. It is all Laplace transform. Okay. So let us, so I told you yesterday that I will start by recalling two things, right? What were those two things? Two very important results, recall and then continue. What are the two results?
Laplace transform about integral and
Yeah.
derivatives.
Yeah, so given a function, its Laplace transform if we know, and mostly we know if we assume piecewise continuity together with exponential order. That's a good set of conditions. And then we know it exists. It might exist without that also, as we saw yesterday, but certainly under this it exists. We say that these are sufficient conditions, need not be necessary. And then we are interested in Laplace transform of the derivative of f, or the second derivative or the nth derivative, etc. if f is differentiable. We are also interested in Laplace transform of the integral. What did you notice about derivative? Laplace transform of the derivative, suppose under all the correct hypothesis, Laplace transform of the derivative is related to the original Laplace transform. How?
Multiply by s.
Multiply by s if you are taking first derivative. If you are taking thousandth derivative, multiply by
Power 1000.
over 1000. There will be some other factors. F of 0,
minus
f
f
by
of
0, etc. appropriately multiplied. Now, what about the integral? If derivative is multiplication by s, what should be the integral? Laplace
division
Divide by
Division by
s.
s.
divide.
division by
Because,
s.
and this matches well with your intuition because integral is antiderivative. So if you're multiplying by s, then 1 by s comes. So it's all very beautiful, very nice. Okay. So this is recalling. These were the conditions. F prime is piecewise continuous on a closed interval 0 to a for all a, and you are assuming exponential order of, what is the definition of the order of this function? In K, M, and alpha, which one is called the order of f?
Alpha.
Alpha. And where is Laplace transform? Where does Laplace transform exist? In the next line,
Greater than.
the region s bigger than
Alpha.
alpha. If s was a complex number, then what will be the condition? Real
Real
part of
part
s
of
bigger
s
than
greater than real part of
alpha.
alpha.
Very good. Okay. So this exists and it is given by s times LF minus f of 0. And we have the corollary for nth derivative. How did you prove the corollary? What is the key word if you have to give me one word?
Induction.
Induction.
Assume up to n minus 1 and then you can prove it for n, and therefore the condition has to be n minus first derivative also you have to assume is piecewise continuous and exponential and of exponential order. Okay, and see, for all this you have to assume exponential order. Not just that, it has to be of the same order alpha. F prime, etc. all are of the same exponential order with the same order alpha. Then you can apply induction and then you get this particular thing. You can see the last line, no? Is it going below? No, right? You can see, no? S power n LF minus S power n minus 1 f of 0 up to Fn minus 1 0. And this will be very useful in IVPs. Let me state the theorem for integral. Integral, let f be piecewise continuous, and suppose this means it is of exponential order alpha, and then the integral is 1 by s integral if you take Laplace transform. So this is a function of t. This is a function of t because I'm integrating 0 to t, and its Laplace transform is 1 by s LF. And what was the key idea of proof here?
Integration by parts.
Fundamental theorem of calculus.
Yeah.
And the key idea of the proof of the previous theorem was integration by parts. Integration by parts proved the result for derivative, and then fundamental theorem of calculus, converted the question about integral to the question about derivative, and then we proved like that. Okay. So now let us continue. The first observation is, suppose f is piecewise continuous on all 0 comma alpha, meaning on 0 comma alpha for all alpha positive, and also assume it is of exponential order. Then we are going to claim that, so what is the difference between the definition of exponential order and this claim? What is the difference?
So there is no M here.
There is no stage, there is no M. I am claiming this to be true for all 0, okay, for all t bigger than 0, and this is easy. Why is that true? Because exponential order implies there exists a k1 and a such that beyond that state this is true. Agree? This is the definition of exponential order. And 0 to that stage you take. 0 to that stage it will be bounded. No? Why? By some constant k2. Why? What is the keyword here?
Closed function and continuous.
Yeah, so piecewise continuous, and therefore on finitely many subinterval it is continuous. By extreme value theorem, there will be a bound on those finitely many. You take the maximum of those bounds, and that bound will work throughout the for the function. So because of piecewise continuity, you can apply extreme value theorem, and therefore you get this to be bounded on 0 to m. Now this k2 can I convert into a constant times e power at? This a is fixed already. Okay, a is given to me, and using that a, I might change this constant k2 to k3, and I will say that on 0m also it is less than or equal to some constant times e power at. That is obvious. What you do is you take k3 such that k2 by k3 is the minimum. See, this is a closed interval, so you can take minimum, maximum, all these things of continuous functions. E power at is given to you. You take the minimum and change that constant to k3. Okay, so it's a small thing. You can check it if it is too fast. So you are getting ft less than or equal to k1 e power at beyond the stage m, and up to the stage you are getting less than or equal to k3 e power at. Is this done? What will be your k now?
Sir,
You take k to be the, yeah.
in between 0 comma n, why f of t should be bounded?
Because of continuity.
I mean, it can go like 1 by x, no? Or isn't?
No, that's why I'm including 0 here. I'm assuming continuity throughout 0m, including 0. Okay. So if take 1 by x or 1 by root x, etc., it is not piecewise continuous, because piecewise continuous means discontinuity is a jump discontinuity, and jump discontinuity means a finite jump. So if you take the function f of 0 equal to 1 and otherwise 1 by x, that is not piecewise continuous in my definition. Is that okay? Because the jump is 1 to infinity, that's not finite. So it's not a jump discontinuity. Is it okay?
Okay, sir.
Yeah. So piecewise continuity will give you infinitely many interval continuity, and a continuity with that boundedness. Okay. That is part of this definition of piecewise continuity, because only jump is the. So you get ft less than or equal to k1 e power at beyond m, and ft less than or equal to k3 e power at, same a, that is the point, same a up to m. So how will you get this? Take k to be the bigger among the two. So take k to be the maximum of k1, k2. So the point is, once you have piecewise continuity together with exponential order, then throughout you can do this. Exponential order is not enough to conclude this. You are also using piecewise continuity. Okay. So for all t positive, this is true. And this has a use. This has a wonderful use. This slide is going to be very, very important. This slide, I'm muting everybody. You can unmute when you want to talk. So, with that observation, we are going to do a very wonderful calculation here. I'm going to do, I know that Laplace transform exists in some region, right? Because it is piecewise continuous and of exponential order. Now take the modulus of the Laplace transform. This will be modulus of the integral, which is less than or equal to integral of the modulus. All of you agree? Modulus of the integral is less
Yes,
than or
sir.
equal to integral
Yes,
of the
yes.
modulus. Now, what do you know about mod of ft? So this is mod e power minus st. I'm taking s to be a real number, and even otherwise, mod e power minus st is this is anyway mod e power minus st times mod ft. What do I know about mod ft? Mod ft is less than or equal to k e power at throughout t positive. So throughout I can apply that. So k comes out and I'm getting 0 to infinity e power minus of s minus a t dt. Okay, what is that integral? It is k by s minus a. Okay, so I'm getting a bound for the Laplace transform. I'm getting a bound for the Laplace transform. And the most important, and of course, I'm using s is bigger than a in order to take this limit as usual. Okay, so s is bigger than a. I'm getting this bound for the Laplace transform. And I'm going to apply the following. I'm going to take limit as s going to infinity. So if you take limit as s going to infinity, that is less than or equal to this limit. But what is this limit? K by s minus a as s goes to a is a given constant, k is a given constant, fixed. So as limit s goes to infinity, what is the right hand side?
0, approaching
0.
0.
That means modulus of this is less than or equal to 0. That means this is going to 0, right? So the limit of the Laplace transform as s goes to infinity has to be 0. Okay. Now an important remark is that, so what is the condition on f in order to prove this? We have actually proved this. What is the condition on f? Condition on f is, it is piecewise continuous with
Exponential.
exponential order. And the conclusion is Laplace transform exists. Not only that, limit s going to infinity of the Laplace transform is 0. Okay, that's what we have proved. Important remark, this limiting behavior is true for any f such that LF exists. You don't need piecewise continuity with exponential order. Whenever LF exists, this property is true. LF of s limit as s going to infinity is 0. Okay. So even without assuming piecewise continuity, exponential order, etc. Proof is tough. We have already proved under that assumption. In general, the proof is difficult, so we won't do it, but you can always believe this. Okay, you can take this for granted. If LF exists, what is f here in this? So in this statement, you said f is a function which is piecewise continuous of exponential order. What is f here? What is the meaning of any f?
Function which does not have that criteria of
Correct. But what is f here still? What is f? What is the notation f? It is a
Function.
function defined on
0 to infinity.
valued in
All
valued
of
in R for us, but in your engineering course, it could be valued in C also. It may not matter. Okay, for us, valued in R. So the point is, it is a function. Okay, it is a function. You know what a function is from your school. It is a function. Okay, for any function such that LF exists, this is still true. Proof is tough. We will skip it. Now, next important remark. So if you take, if I ask you to find the Laplace, inverse Laplace transform of s minus 1 by s plus 1, what is the answer?
does not exist.
Does not exist. Inverse Laplace transform does not exist. This is not the Laplace transform of, by whatever we have proved, you can conclude that this is not the Laplace transform of any function which is piecewise continuous and of exponential order. If you assume this result, you can say that this is not the Laplace transform of, complete the sentence,
Any
Laplace
function.
transform of any
function.
function. Same with this, e power s by s, what is the limit as s going to infinity?
Infinity.
Correct. S square, what is the limit?
Same, infinity.
S by log s?
Infinity.
So none of this, and here what is the limit? S minus 1 by s plus 1?
1.
1. So none of this thing is 0. Therefore, none of this is our Laplace transforms of any function. Do you notice anything in this remark? Something that I have stressed? Again and again, I am stressing this. Okay, any function. So I have written here, note the underline to stress the word function. Do you have any clue as to what I am hinting at? Why I am stressing function so much?
Sorry, no.
Because we sometimes define things like Dirac delta, which are not really.
Absolutely. You are engineering students. In application, you don't quite care about function. You want to, get things done. And sometimes, you will define Laplace transform not just for a function, as in the mathematical sense. You might also do it for a typical thing like Dirac delta function. Though we say Dirac delta function, it is not a function. Okay. Dirac delta function is not a function in the mathematical sense, but we will do that also. We will come to that in the either in the next lecture or next to next lecture. For things like Dirac delta function also we will do Laplace transform, and then this condition is not true. For example, the Dirac delta function, if you take its Laplace transform is constant function 1 and limit s going to infinity is 1. So that is possible. Okay, that's why I'm stressing this. This
Sir,
is true only. Yeah, go ahead.
then when we should assume that the limit is true compulsorily,
Yeah.
when we should think, I mean,
What I'm saying is, if you are dealing with usual functions, ordinary functions of mathematics, if Laplace transform exists, limit s going to infinity of the Laplace transform has to be 0. That is true. If it is of exponential order and piecewise continuous, we already gave a proof. Otherwise, I'm stating it as a remark. You can take this for granted. It is a bit difficult for me to prove, so I will not prove. But what I'm saying is, in engineering, in applications, you may also take what are called distributions, not functions. And their Laplace transform, then this condition is not true. That's what I'm saying. Is that clear?
for ordinary functions means
Ordinary function meaning just function. Okay. So what is a function? Let's not get into that. You know what a function is. Okay. But what I'm saying is, you might have seen in physics what is called the Dirac delta function, right? Have you seen Dirac delta function?
yes.
Or you will see, or we will see in this course. That is not
Yes, sir, we have.
That is not a function. Some people will define it as everywhere other than 0, the answer is 0, and at 0, the answer is infinity. Some people will define it like that, which is not quite correct, because infinity, you cannot say something is infinity. So some other people will define it as, integral, so that the integral is 1, etc. under something. We will define it properly. Okay. So the point is that is not a usual mathematical function. I use the word ordinary to say that the usual functions. Okay. We will come back to this. I'm just stressing it right now so that you will not forget it. Okay. Let's solve an IVP. First example is this. So this is an IVP, no? And this IVP anyway, you could have solved easily, right? You don't need Laplace transform. How will you solve this? Because this is constant coefficients. So you can
Assuming
plug in e power characteristic equation, you can solve it and plug in these values and you can get the solution. But let us do it using Laplace transform. How will you do it? What will be your first step?
Take Laplace transform of both
Take
sides.
Laplace transform. Okay. So take Laplace transform throughout and you are going to get L of y double prime minus L of y prime minus twice L of y. Why? Because L is linear. L is linear. So L applies like this. Scalar multiplication and addition, it is linear. So you will get L of 0, which is 0. Now, what is the next step? What is L of y prime? What is L of y prime?
SL of y
SL of y minus L of 0.
Not always, no? Under some assumption. What is the assumption on y so that it is true?
Y is of
continuous
Continuous.
differentiable
And
derivative
y
is
prime is
piecewise.
y is
Y
continuous,
prime is
y is of
piecewise.
exponential order, and y prime is piecewise continuous. Correct? So assume that there is a solution y such that y double prime is piecewise continuous on all 0 alpha. On all 0 alpha meaning on 0 alpha says that for all alpha positive. Okay. And y prime are of exponential order. Assume there is such a solution and continue. This is what you will do.
Sir, we can show that y double prime has to be continuous because y prime and y have to be continuous. So there's
Correct.
there.
That is correct. But I'm just stating exactly as in the theorem. This is not such an important thing. This is just a theoretical step. Assume there is such a solution so that you can apply those formulas. And suppose you are not getting an answer, then come back and do something else. Okay. You assume and then you proceed. If you get a solution, well, good. You can stop it there. If you don't get a solution, you bother about it at that time. As they say, Let's cross the bridge when we reach there. Okay, so assume this. Therefore, L of y double prime is s square Ly minus sy0 minus y prime 0 minus Ly prime is sly minus y of 0 minus twice Ly equal to 0. So you've got an equation, no? You have got the equation s square minus s minus 2 times L of y minus s, because y of 0 you're putting 1, and
Sir, shouldn't it
minus,
be sy prime of 0 and y of 0? Or
you are right. You are right. You are right. S y prime 0 minus y of 0. So I will correct the typo, but is the next step correct? S square Ly minus sly minus 2. This is fine. And the next step will be sy prime 0. So
sir,
that,
actually, I think I might have mistaken. I think this is correct only.
no, this is correct. This is correct. Yeah, yeah. Sorry. So you were confused and I also got confused. Let me just double check.
Sir, it is correct only.
Yeah, it is correct. Yeah. It is sy0 Sn minus 1 f0, Sn minus 2 f prime 0, etc. Okay, so this is correct. Yeah, I also get confused sometimes. That's okay. So this is okay. So this is sy0, which is minus s, minus sy0 is minus s, and minus of minus y0 is plus 1, and y prime 0 is 0. So you are getting this. Therefore, you got Ly equal to s minus 1 by s minus 2 times s plus 1. S minus 1 by s square minus s minus 2. S square minus s minus 2 is s minus 2 times s plus 1, which is partial fractions you can write. And therefore, can you tell me what the answer is? 1 by s minus 2 tells you what is a function?
e to the power 2x.
E power 2t, e power 2x, and 1 by s plus 1 is?
E to the power minus
Minus x.
We have solved it, no? So RHS is this, therefore the LHS is this. So on one, straight away you got the answer. If you were using, your earlier method by a characteristic polynomial, how would you have done it? You would have got the answer to be C1 e power 2t plus C2 e power minus t. And then you would have plugged in y of 0 is something, y prime 0 is something. And you would have evaluated C1 and C2. This is, I like this even more. You're substituting that in the process itself and you are directly getting the answer. Okay, it's a beautiful method and the method is much more powerful. This was a simple example just to illustrate. Method is much more powerful. Many other things we can do. Let's do one. Yeah.
If we know that Laplace, we know that 1 by 1 for the inverse Laplace transform 1 by s minus 2, so we did it.
Yes.
If we got some function which we don't know,
then you can't do.
then we need to go normal method only.
Then you have to try something else. Okay. So
I mean, we can't find out finally. Even it's weird, we can't do something different.
Yeah. So the point is this method will work only if you know how to find inverse Laplace transform. And how do you find inverse Laplace transform? Only from your experience. So only this morning I learned, I did not know. So this will take time. So this morning I was searching some of the literature on Laplace transform. And I saw this formula, which you will not see in any textbook. And there is a reason for that. So I will show you. Okay, so I have not projected it yet, no? So let me share the screen quickly and show this. Sorry, how do I? So I need to stop sharing this in order to show new share should work. Yeah. Can you see the Firefox now?
Yes, sir.
Yes, sir.
Yeah. So here, this is the page called Inverse Laplace Transform. And I did not know this. So should I increase the font? Can you see? So there is what is called Post inversion formula, which I learned only this morning. Okay. Named after some mathematician, Emil Post. But then, I read this line and then I did not read further. It's a simple looking, but usually impractical formula. So there is a formula in terms of, some limit and derivatives, but this is impractical. This is much more difficult to do. But there is a nice looking formula, but it's impractical. Okay, so I did not know about this mathematician also, Emil Post. Yeah, relatively new mathematician, because usually, what we are studying old mathematics, but this is kind of modern by the standards of mathematics. Anyway, so can you see again or the other Screen also is gone now. Okay, so
The
come back.
screen is gone.
Now you can see, no?
Yes, sir.
Okay, so let's continue. So yeah, so to come back, you need to find out, you need to know how to find the inverse Laplace transform, only then the method is successful. Let's do one more example. Y double prime plus y is sine 2t, y of 0 is something, y prime 0 is something. Take Laplace transform. So you will get L of y double prime plus L of y equal to L of sine 2t. Okay, so that this function also you should know the Laplace transform. So therefore you get s square Ly minus s by 0. What line am I? Okay, so this is fine. S square Ly minus s by 0 minus y prime 0 plus Ly equal to, what is L of sine 2t? What is L of sine 2t?
2 upon s square plus 4.
2 upon s square plus 4. Very good. And therefore Ly is this. By the way, I am skipping one line here. No, what is that line which I have not written?
Y is
Assumptions.
order.
Theoretical
Assumptions
part.
on y. Okay, from now onwards, I will not write that. But first time I wrote that. So under the assumptions on y, you can plug in this, and you got this. And so maybe I will not read all this because I haven't done it anyway recently. And you have to double check. If there is a typo, you let me know. So Ly, what all you are doing is Ly, you are putting all these conditions, and you have taken, right? S square plus the 1 Ly equal to, you have put these other things to that side, you have solved it, you got this. So you will write this as partial fraction. This is the method that you know well, and solve for this. So you got the answer to be this. So now can you guess what is y? S by s square plus 1 tells you what?
And
Sine t.
Therefore,
sine
this whole thing is 2 cos t.
Cos
And 1 by s square plus 1 is
5 by 3 cost.
5 by 3 sine t
t.
5 by
5 by
3
3 sine t.
minus 1 by 3
And 2.
into
Sine
sine
2t.
2t.
sine 2.
Sin 2t.
Very good. So 2l cos t plus 5 by 3 l sine t minus 1 by 3 this thing. Therefore, yt is 2 cos t plus 5 by 3 sine t minus. Very good method, no? Straight away you are getting the answer. Okay. So very, very important. Inverse Laplace transform, you have to be absolutely confident and comfortable. If you, change S and A, if you misunderstand, or sin t or cos ht, if you misunderstand, your answer is wrong. Okay, you have to be very, very careful. I mean, you should know it by heart. It's like, if I ask what is 7 into 7, then you know 49 without thinking. Like that, you should know Laplace transform and inverse Laplace transform. You should not be, thinking about it. It should be, by heart. Okay. So yt is this. And next example. Okay, I'm not giving a differential equation. I want you to solve this. L of f is this. How do you do the inverse Laplace transform? What strikes you here?
Partial fraction. Separated as fractions.
Okay, partial fractions you can do, and I think the point of this slide is to do it in another way. Can you get another way? 1 by a square plus a square, no? 1 by a square plus a square,
Integral of.
Yeah, correct. So what is 1 by a square plus a square? What is the inverse Laplace transform?
Double integral.
No, I forget a square. I'm just saying 1 by, no, I cannot highlight just this part. Forget this a square part. If you had 1 by a square plus a square, what is the inverse Laplace transform?
1 by
Sin
a
80
sin
by
square.
1 by a sin 80. Now suppose you have 1 by s into that. How do you get it out of the original?
Partial fractions.
No, I am not talking about partial fractions. That is correct.
Integral.
multiply by t.
Another method.
Multiply by t.
We integrate.
Integrate, right? Because what is your result here? The first result that we recalled. The second result that we recalled. This is differentiation, and for integration, see, if you have 1 by s LF, what is its L inverse? It is integral of fx dx, 0 to t. Agree? If you know LF, and then if you divide LF by s, then the inverse Laplace transform of that is integral 0 to t fx dx. So this is, I just wanted to show you another method. Who knows which method will be, faster or more useful. So here, doing via that method, because this answer is this, L inverse of this is integral 0 to t of sine ax by x dx. And that you can do. And how will you do now? L inverse of 1 by s square. Do the same thing again. You have got this answer and integrate that from 0 to t. 1 minus cos ax by a square dx, integrate from 0 to t, whatever you get as the answer. So you could have done by partial fractions, but here is another method. Sometimes this may be better. I don't know. It depends on, you are solving more problems. Is this absolutely clear to everybody? Should I repeat? If there is anybody who did not understand this method, these are all very, very important methods. If somebody who did not understand this, please tell me and I will repeat it. So the point is, here you have got L inverse to be this, and therefore L of this is this, and LF by S. LF by S is the answer for integral 0 to t fx dx. So that's what you're using. LF by S. This you are thinking of as LF by S. And therefore the answer is integral fx dx. And fx is this. And do it once more. Okay, so that's a good method. So f of t is this. And let me do one more result. Easy result. Suppose f is piecewise continuous and of exponential order. So this is another thing, right? Earlier what we have done is, we took the function small f and then we took the derivative with respect to t, of course. F is a function of t. We took derivative with respect to t and then we took its Laplace transform. Here what I'm doing? Here I'm taking the Laplace transform, which is a function of the variable s, and I'm taking derivative with respect to s. And that also has a nice answer. So earlier, what was your observation? When you took the derivative and then took the Laplace transform, that involved multiplication by s, right? When you took the function f of t and then you took the derivative f prime t and then you took the Laplace transform, that involved taking the original Laplace transform and multiplying by s up to that constant minus f of 0. Here also, derivative involves multiplication, but multiplication comes inside. So when you take Laplace transform and then when you differentiate with respect to s, that is same as the Laplace transform of t times ft with a minus sign. Okay. So derivative results in multiplication. If you take derivative first and then you take the Laplace transform, it is multiplication by s. If you take the Laplace transform and then take the derivative, it is multiplication by t, but inside the parenthesis, inside the bracket, before taking the Laplace transform. So this is easy. The proof is very easy. You just do it. F of s is, this is the definition. So you can compute dfs by ds. No, how do you do this in your, when you were preparing for JEE, you would have been experts in this method. What is this method called?
Leibniz formula.
Newton-Leibniz.
Is it called that? So I did not know that. It is also called
Feynman.
differentiation under the integral sign. Maybe, whatever you said also means that. So what is dfs by ds here? You can take the derivative under the integral sign. So it will be integral 0 to infinity. Why do I put partial? Because there are two variables. So I want to say that it is with respect to s. So del by del s of e power minus st ft dt, right? You must have done this kind of integration. And this is minus t e power minus st ft dt. That is exactly this. So it's very easy. Okay, it is just differentiation under the integral sign. So how to justify this interchanging? This is what you have done in calculus. And I have just copy pasted the result from Wikipedia. Much more general result. Okay. Here it is a simple situation, and more generally, this is just copy pasted from Wikipedia under this title, differentiation under the integral sign. And so suppose you need to differentiate this function f of xt dt, and what is varying from ax to bx here? What is varying from ax to bx? T is varying from ax to bx. And this is more general because ax and bx are now functions. Here, I am applying to constant 0 and How do I apply to infinity? I will apply to 0 to b that formula, and I will take limit as b goes to infinity. Okay, that's how I apply it here. So here ax is a constant, bx is a constant. That's where I have applied, but more generally it is true with respect to x. And suppose you know that this function f of xt and partial with respect to x, both are continuous in both t and x in some region in the tx plane, including this kind of a rectangle, and you have nice conditions on these functions ax bx also, and then you can differentiate. And what is the answer? D by dx of fx is f of x comma bx times b prime x minus f of x comma ax times a prime x plus integral ax to bx del by del x fxt dt. And this you can prove using using fundamental theorem of calculus. Maybe you have already proved this in calculus course. I don't know. Have you seen this in calculus course in this generality? Or maybe even in plus 2, have you seen this in plus 2 before coming to IIT?
Yes. Yes.
You have seen this. So some of you have seen this, some of you might not have seen this, but anyway, this is a very useful formula. And this, you know, this will solve you know, you can also use this to find integral in very nice ways, and this is a very powerful technique. And let me just show, you know, on the Wikipedia page there is a very nice story. Differentiation under integral sign. It was certainly there long back. I hope it is still there. So once again I need to share this. No, this is some brilliant tutorial. I don't want this. I want Wikipedia. Differentiation under integral sign wiki page. Can you see the screen? Yeah, so somebody who said Leibniz integral rule is absolutely right. That's what Wiki is also saying. So this is the formula that I have written down. Now, can you see the Firefox page?
Yes.
Can one of you confirm?
Yes, sir.
So this is exactly what I have copied. Okay, but what I want to show you is not that. So, okay, there is something called in popular culture. Yeah. Yes. So, you know, I think we don't have time. So you please read this. Okay. So I will just put it in the chat. So there's a very nice story about the famous physicist Richard Feynman, which he is recalling in his famous book. Surely you are joking, Mr. Feynman. You will like this. So you read it later. Okay. So let me don't do that right now. There is no time. Can you see my slide again?
Yes, sir.
Yes.
Okay. So I will just share the link. How do I share the link? Yeah, it's there. The link. Can you see the link in the chat?
Yes, sir.
Okay. So you can click and read it later, not right now, or right now if you want. So this is the result that we are applying here. So that slide is the justification for this step. But this step anyway you would have done based on your +2 experience. Okay. So that gives a proof of this nice formula. And this is the theory behind that. And be comfortable with this slide also. You know, I can ask tricky questions where you need to know the full power of this formula. Maybe, I don't know. I'm not thinking about a question right now. But if you challenge me to ask tricky questions, I can do tricky questions. You know, that is, I'm quite comfortable in making the questions tricky. I may not be good in answering those questions. But as a teacher, I'm certainly good in asking, in trying to coming up with tough questions, especially in this topic. Okay, so let us do some examples. 1 by s square plus beta square whole square. So here, what strikes you is, so you know your intuition has to build. So what strikes you here is s square plus beta square. That is what you know. S square plus beta square. With that, you know two things. You know s by s square plus beta square is cos beta t, and beta by s square plus beta square is sin beta t, and therefore you can apply that thing. Because what you know is If you multiply by t and then take the Laplace transform, that involves derivative on the Laplace transform. So if you are going to get s square plus beta square whole square, that tells you, right? How do you get square in the denominator? By taking derivative, no? 1 by s square plus beta square. If you take derivative, that will result in s square plus beta square whole square. Some more things may come, but certainly you can get the square in the denominator by taking derivative with respect to s. So that's your observation. Therefore, L of t cos beta t is minus d by ds of s by s square plus beta square. When you do that, you get this. And L of t sin beta t is this, and you got this. And therefore, this you can get using these two. So multiplication by t inside is what solved the problem for you. So you get this. So L inverse of s by s square plus beta square whole square is s by s square plus beta square whole square is t sin beta t by 2 beta. Clear? S by s square plus beta square whole square. This 1 by 2 beta you can do here. So 2 is getting solved first. 2 is getting solved first. You get t sin beta t by 2 beta. And the first one, how do you do now? This is, what did you do here? What is the technique here? What you know is, this you know the answer. S by s square plus beta square. And now what you're doing is, this is this divided by s. So that means you can integrate this. Maybe I should have asked you before showing it. But anyway, you know, it came in the slides. Is this step clear? Having solved this, 1 by s square plus beta square whole square is s by s square plus beta square whole square times 1 by s. So you can apply that integral formula. Laplace transform divided by s. So this is this Laplace transform of this, Laplace transform of this divided by s. So this will be integral 0 to x, 0 to t, x sin beta x by 2 beta dx. So when you do that, you will get that. And how do you do L inverse of s square by this?
By using that cos beta t and this result.
Differentiating.
Yeah, you can do by differentiating, right? Because
can overlap
s times LF is L of f prime. You can use that.
No
Okay,
need.
so this is d by dt of t sin beta t by 2 beta. And why not, you know, minus y of 0? Why not that term? So my answer will be d by dt of, so what was my formula? My formula is L of, no,
L of f dash
which formula am I applying? Multiplying by s, right? Multiplying by s is L of f prime, no? This is multiplying the Laplace transform of this by s, right?
Yes, sir.
So multiply. So my formula is s times the Laplace transform minus f of 0, right? Minus f of 0. That is,
Here it is 0.
yeah. So I'm using the fact that f of 0 is 0. That's why that thing did not come here. And once again, since I got confused, this is s times Laplace transform of f, where f is this function. Agree? F is this function where my cursor is moving. And then this is s times L of f minus f of 0. But s times L of f minus f of 0 is what? It is L of f prime. No. S times L of f minus f of 0 is L of f prime. Correct. And I'm doing L inverse. So you just have to do f prime t. That's what I'm doing on the right side. D by dt is f prime. Okay. So whatever the answer is, that is the answer. So you get these two things. Okay. So this is the last slide for today. And it is time. So let me stop sharing. So could you read that story about Feynman? We have 3 minutes. Should we read it together, or anyway, I can stop recording. So let me stop recording.